Welcome to the online course on pericyclic reactions and organic photochemistry. We are now in module 10. We have so far seen Diels Alder reaction, the basic aspects of Diels Alder reaction, the regio and stereoselectivity aspects also we have seen. Now it is time to see some examples of how Diels Alder reactions are used in synthetic applications in the synthesis of some fascinating organic molecules. Now, Diels Alder reaction initially gives a 6-membered carbocyclic ring or a 6-membered heterocyclic ring, depending upon whether we are doing a carbon-based diene and dienophile or heteroatom-based diene and dienophile. Now, it can also produce bicyclic compounds if the diene or the dienophile is already cyclic in nature. Now, the product of Diels Alder reaction, namely cyclohexene and the cyclohexadiene, can be aromatized by dehydrogenation reaction using various reagents. So it is not that it produces only a 6-membered ring which is a cyclohexene ring. It can also produce a 6-membered ring which is a benzene ring by a suitable mechanism of dehydrogenation using various reagents. The bicyclic compound that are produced by Diels Alder reaction can also be converted into cis-1,3 disubstituted cycloalkenes. Here is a nice example of that. Let us assume the Diels Alder reaction between this dienophile and the diene proceeds to give this particular 2-to-1 bicyclic norbornene type of a structure. Now, upon oxidation or by ozonolysis, this double bond can be cleaved, and that will result in the formation of a 1,3 cis dialdehyde, cyclopentane dialdehyde of such sort. Now, depending upon the stereochemistry of the 2X groups in this dienophile, the 2X group can be either cis or trans, or they can be endo or exo. Assume they are cis and they are endo in nature, then all these 4 functional groups in this cyclopentane will be having the same stereochemistry, relative stereochemistry, namely all cis stereochemistry is what one would have. So it is not that Diels Alder reaction can produce only stereoselectively 6-membered ring system. That 6-membered ring system so produced can be manipulated to a 5-membered ring system in a stereoselective manner. Now, why does this ozonolysis produce the cis isomer of the dialdehyde? That is because the 2 carbon-carbon bonds are pointing in the same direction downwards, and as a result of that, the ozonolysis essentially produce the relative stereochemistry of the 2 aldehyde to be cis with respect to each other. Now, the relative stereochemistry between the aldehyde and the X group will depend upon whether you have a endoselective addition or an exoselective addition. All likelihood, the endoselective addition will be the predominant product. So, that would mean this aldehyde and the 2X group and the other aldehyde will be all cis with respect to each other in this type of a situation. On the other hand, if it is a exoselective product formation, then the aldehydes and the 2X groups will be trans with respect to each other. So, both the stereoisomers it is possible to produce using the Diels Alder reaction. Now, let us take a beautiful example of barralene. This molecule is called barralene because it is supposed to look like a barrel. It is essentially a 2-2-2 bicyclic system, bridged bicyclic system. Retrosynthetic analysis will tell you that this molecule can be produced by a Diels Alder reaction between benzene and acetylene. Of course, benzene does not undergo Diels Alder reaction readily, and so does acetylene. It does not undergo the Diels Alder reaction quite readily. Both of them are very inert compound, and they don't undergo Diels Alder reaction between themselves to produce barralene. So, how do we produce barralene? In an indirect manner as shown in this particular scheme. Now, take the valence isomerization of oxapine to benzene oxide. So, this is essentially an electrocyclic ring closing reaction. Under thermal conditions, certain amount of the concentration of the benzene oxide form exists in the oxapine structure. So, that undergoes Diels Alder reaction much faster than the oxapine itself. So, this behaves like a diene, and the endoselective Diels Alder reaction essentially produces this 2-2-2 bicyclic framework that is necessary for the barralene synthesis. Now, this is a disulfone substituted derivative, sulfonyl substituted derivative, and that is acting as a equivalent of acetylene in this particular synthesis, as we will see soon. Now, all you need to do is get rid of the functional group and introduce a double bond in this position, and also introduce a double bond at this position. Now deoxygenation is what is necessary to be done of the epoxide to produce this olefin, and this is best performed by low valent tungsten kind of a compound. The tungsten hexachloride, tungsten is in the maximum valency. When it is reduced with a strong butyl lithium kind of a reducing agent, it will go to low valent low valent tungsten, and the low valent tungsten is very oxophilic and it is capable of removing this oxygen and go to tungsten oxide. So the low valent tungsten that is produced by the reaction between tungsten hexachloride and butyl lithium at low temperature essentially deoxygenates this epoxide to produce this olefin. Now all you have to do is do the desulfonylation reaction, or the desulfonation reaction is what it needs to be done. This is best, the carbon sulfur bond is best treated with reductively cleaved by usage of the sodium amalgam in methanol. So reduction of sodium amalgam in methanol produces a carbanion at this center by the cleavage of the carbon sulfur bond, and the carbanion so produced undergoes 1,2 elimination of the other sulfone derivative as a phenyl sulfenate. So the elimination of phenyl sulfenate, 2 moles of phenyl sulfenate essentially produces a double bond over here. So this is a beautiful synthesis of 2,2,2 bicyclic compound which is called barralene. What could not be accomplished in a direct manner is accomplished in an indirect manner, quite elegantly so. You can see here the yields of the individual steps are nearly quantitative, 90 plus yields is what is obtained. So barralene can be conveniently synthesized by this particular methodology. So here is an example of the power of Diels Alder reaction in terms of producing the basic framework of the barralene, which is a 2,2,2 bicyclic framework. Here is an example of a propeller shaped molecule called triptycene. This molecule is a 3-blade propeller shaped molecule. This has a C3 axis of rotation passing through the front sp3 carbon and the backside sp3 carbon. Such a molecule can be produced by a Diels Alder reaction as illustrated in this particular example. Now the basic propeller framework is designed and synthesized by the cycloaddition reaction of anthracene and benzoquinone. Anthracene is a very reactive diene. The 9 and 10 positions of anthracenes are quite reactive. They behave like a typical Diels Alder diene, and they undergo Diels Alder reaction across the 9 and 10 position. In doing so, they produce a double bond at this position which completes the sextet of this particular ring. So instead of anthracene having only one sextet, upon Diels Alder reaction it produces 2 sextet or 2 individual benzene rings, which is probably having a higher resonance energy than anthracene itself. That is one of the reasons why the 9-10 positions of anthracene are extremely reactive towards Diels Alder reaction. The reaction of this molecule with the benzoquinone essentially produces the necessary framework for this molecule, and the reduction and elimination of hydrogen peroxide in this molecule essentially produces this triptycene molecule, which is the benzanulated 2,2,2 bicyclic system of this kind. Now this is a cage type of a molecule that also can be produced by a Diels Alder reaction in combination with the 2,2,2 cycloaddition reaction. So the initial thermal 2 plus 4 cycloaddition reaction, or the 4,2,2 cycloaddition reaction in a suprafacial manner and in an endoselective manner will produce this particular molecule. The 2,2,1 bicyclic framework is essentially produced because of the fact that your diene is a cyclic diene, and the cyclic diene produces the bridged bicyclic system, and the structure of this is shown here. This is an endo product. In other words, the benzoquinone moiety essentially lies underneath the 2,2,1 bicyclic framework that brings this double bond in close proximity to this double bond with a distance separation of less than 3.5 angstroms or so, and as a result of that the 2,2,2 cycloaddition reaction between these two olefinic system is quite facile. So under photochemical condition, this molecule undergoes a 2+2 cycloaddition reaction, forming the cyclobutane ring, which is this particular cyclobutane ring in this molecule. And now decarbonylation followed by elimination of one of the methylene group essentially can produce a cubian kind of a structure, which is a caged molecular structure that we have here. A similar caged molecular structure is also known as basketene. This is a very interesting molecule. This double bond is supposed to be the handle of a tilted basket as it is drawn in this particular shape. Now this molecule is synthesized using this particular methodology shown in this particular slide. The cyclooctatetraene undergoes valence isomerization by means of an electrocyclic ring closing reaction under thermal condition to give this fused bicyclic system, where you have a cis fusion of the bicyclic system. and this is again a diene. So this can undergo a Diels Alder reaction. Compared to cyclooctatetraene, this will undergo Diels Alder reaction much faster because this is a 6-membered diene compared to an 8-membered ring system, which is this particular ring system. Cyclooctatetraene does not undergo Diels Alder reaction. So the valence isomer, which is a cyclohexadiene unit bicyclic compound, undergoes Diels Alder reaction with maleic anhydride in an endoselective fashion upon heating, and this endoadduct is what is necessary for the formation of the caged compound, because in the endoadduct this cyclobutene ring and the cyclohexene ring, these two double bonds are face to face with respect to each other. So they undergo a very facile 2pi cycloaddition reaction under photochemical condition. So the first step, Diels Alder reaction, is a 4pi suprafacial 2pi suprafacial cycloaddition reaction. The second stage is a photochemical 2pi suprafacial 2pi suprafacial cycloaddition. Such a cycloaddition essentially builds this cubane structure in this molecule. Now all you need to do is hydrolyze the anhydride to the dicarboxylic acid, and the dicarboxylic acid can be oxidatively decarboxylated to give this olefin using lead tetraacetate as an oxidizing agent. Lead tetraacetate is a powerful oxidizing agent, so it oxidizes the carboxylic acid to the corresponding radical by decarboxylation. So as a result of that, the oxidative decarboxylation of this diacid essentially produces this olefin, which is the basketene in this structure. This is a very elegant synthesis of a 2,2-paracyclophane derivative. Several 2,2-paracyclophane derivatives have been synthesized using strategy. The starting material is essentially a bisalene. This is a hexatetraene is what is the starting material, and it behaves like a diene, Diels Alder diene, and reacts with acetylene to produce the paraquinodimethyl derivative. Now this is the concerted step that we are talking about, namely the 4pi 2pi suprafacial cycloaddition reaction between the bisalene and the acetylene moiety produces this disubstituted quinodimethyl derivative. The quinodimethyl derivative, paraquinodimethyl derivative undergoes a dimerization reaction to produce this particular 2,2-paracyclophane derivative. The quinomethyl dimerization itself could be a radical pathway because considerable amount of polymer is also produced as the byproduct in this reaction. So the only step that is pericyclic in nature is this particular step, where the 4pi 2pi cycloaddition reaction is taking place between the bisalene and the acetylene. So this is a very elegant synthesis of a fairly complex structure, which is a 2,2-paracyclophane derivative in this particular case. Here is a very fascinating example of a belt-shaped molecule. This molecular structure, although it is drawn in a planar form, it actually is a belt kind of a molecule, a loop kind of a molecule, where all these oxygen atoms are protruding out of the belt. In other words, this particular molecule has a belt shape in its structure, and that can be synthesized using the strategy that is shown here. The starting materials are A and B. These two molecules are the starting material molecule. This molecule, because of the oxo-bridged 2-to-1 bicyclic framework, they have a curved shaped curvature of the molecular structure. The arrow essentially shows the curvature of this particular molecule. Similarly, this molecule B, which also has two oxa 2-to-1 bicyclic framework, the oxygens are missing here. I am sorry, this should be oxygen here, and that is also a curve shaped molecule. So when this behaves like a diene and this behaves like a dienophile, so this can undergo 2 times Diels Alder reaction. This can also undergo 2 times Diels Alder reaction. So if the molecule undergoes Diels Alder reaction in a 1:1 ratio, this will essentially produce molecule C. You can see here the red colored portion of the molecule is the coming from compound A, and the lilac color portion of the molecule essentially comes from molecule B. So this is a 1:1 cycloadduct. Diels Alder adduct of the two compounds is what is shown as structure C. On the other hand, a 2:1 cycloaddition product is also shown here. This product is formed in 24% yield, and this product is formed in 61% yield when these two molecules are refluxed in toluene for 12 hours. Here you can see here the molecule A, two equivalents of the molecule A has undergone twice Diels Alder reaction, once in this side of the dienophile, once on the other side of the dienophile, resulting in the formation of the bis adduct in this particular case. Now This molecule can undergo dimerization. A cyclodimerization is what is taking place. This portion has the diene and this portion has the dienophile. So two molecules should line up such that the dienophile portion of the second molecule should lie close to this, and the dienophile portion of the second molecule should lie close to this. Such a Diels Alder reaction is very unlikely to happen because it is a orientational problem that you have in this particular structure. Nevertheless, it produces the beltene in about 3.5% yield. On the other hand, if one takes this molecule and treats it with further one equivalent of the compound B, it can undergo Diels Alder reaction on this side as well as on this side. Because this molecule is already having a large curvature, it can undergo cyclization, and such as Diels Alder, double Diels Alder reaction on either side of the molecule which are behaving like diene with this molecule which is behaving like a dienophile, this portion as well as this portion behaves like a dienophile, it produces this cyclic structure in about 20% yield. Although this Diels Alder reaction is carried out at a high pressure and around 60 degrees or so, with a 9 to 10 kilobar pressure is what this Diels Alder reaction is carried out. So such a fascinating molecule has been generated by a multiple Diels Alder reaction in this particular example. Now when cyclopentadiene undergoes Diels Alder reaction with the parabenzoquinone, the parabenzoquinone can actually undergo Diels Alder reaction twice, once on this particular side, another time on this side. In doing so, it initially produces an endo isomer of the monoadduct. The endo isomer of the monoadduct in the presence of excess of cyclopentadiene can undergo once more Diels Alder reaction to produce the other side to be an endo isomer of the product. So essentially you produce a cis anti-cis kind of a fusion in this bis adduct of the benzoquinone molecule with cyclopentadiene as the diene. If you take the parabenzoquinone which is differentially substituted, one side is substituted with a methoxy, the other side is substituted with a methyl, it undergoes Diels Alder reaction with butadiene, for example, on heating to 100 degrees. Now between this dienophile and this dienophile, this is a more reactive dienophile because this is electron deficient in relation to the electron rich dienophile, which is this particular dienophile. The methoxy, the oxygen lone pair on the lone pair present in the oxygen of the methoxy functional group can delocalize itself onto this double bond, thereby rendering this to be a relatively speaking electron rich dienophile compared to this dienophile on the other side. So the Diels Alder reaction takes place in a very regioselective manner only on this particular side, resulting in the formation of the corresponding Diels Alder adduct, which is shown here, for example. This molecule is taken as an intermediate in several step synthesis of cholesterol and other natural product by Woodward. Here is another example of a Diels Alder reaction where you have a electron withdrawing substituted diene as well as dienophile. The reaction proceeds in refluxing benzene, although in very poor yield, for example only 27% yield or so, because this is a deactivated diene, it's not an electron rich diene. Unlike, for example, butadiene, this has an electron withdrawing functional group. That may be the reason why the reaction is very sluggish in this particular case. It also produces the endoadduct, which is shown here, for example, and this molecule is a key intermediate in the several step synthesis of reserpine, which is a naturally occurring alkaloid molecule. So the rest of the synthesis is fairly complex, which is very well known in the literature. All I wanted to do here is to point out the fact that the intermediate can be converted into several other natural products in these two examples from the Diels Alder reaction of a diene with the parabenzoquinone as the dienophile. Here is an example of a synthesis of a naturally occurring molecule reserpine. Reserpine is again an alkaloid. This is a construction of ring D and E of reserpine is what is being shown in this particular case. Now the Diels Alder reaction is essentially between the dihydropyridine, this particular molecule which is a starting material acts as a diene, and this acts as a dienophile. This is a alpha acetoxy acrylate, is methyl acrylate is what is acting as a dienophile. It produces a 2:1 ratio of the two isomers that are possible for the Diels Alder reaction depending upon the orientation of the acetate and the carbomethoxy functional group. One is an endo, other one is an exo type of an adduct. With respect to the carbomethoxy group, this is an endo product. With respect to the acetoxy, this is an endo product, for example. In a 2:1 ratio, this is produced. This undergoes a Claisen-Schmidt kind of a condensation reaction to produce a beta keto ester. You can see here the lithium enolate that is generated from tertiary butyl tertiary butyl acetate, for example. By treatment of tertiary butyl acetate with the LDA, this can be produced. This reagent essentially adds on to the carbonyl functional group of the ester to produce the corresponding beta keto ester in this particular case. The beta keto ester can be converted into the corresponding methyl ether, and now this molecule is set up to undergo a 3,3 sigmatropic rearrangement. We will consider the 3,3 sigmatropic rearrangement at a later stage, but this crucial intermediate is essentially obtained by the Diels Alder reaction of these two molecules to produce these two Diels Alder adduct, and the two Diels Alder adduct can be converted into the corresponding 3,3 sigmatropic system, which undergoes 3,3 sigmatropic system rearrangement to produce this fused bicyclic compound. This portion of the reaction we will consider it when it comes to the 3,3 sigmatropic rearrangement. I will explain it properly at that time. Now, orthoquinodimethyl is an extremely reactive diene. This portion of the molecule can essentially react as a diene in producing a benzene type of a structure. In other words, the driving force is essentially the aromaticity of this particular ring, aromatic ring that is produced by the Diels Alder reaction. The orthoquinodimethyl itself can be generated in several ways. Starting from here, let us consider the thermolysis of a benzoyclobutene, which is already seen in the electrocyclic reaction to produce the corresponding orthoquinodimethyl. In this particular case, a dehalogenation reaction is promoted by sodium iodide or potassium iodide. So, when this orthodibromomethyl compound is taken and reflects with sodium iodide in acetonitrile kind of a solvent, it triggers the elimination of bromine by the 1,4 elimination of bromine, for example, to produce the orthoquinodimethyl. This sulfolane molecule, which is a benzo-fused sulfolane molecule, undergoes thermolysis to eliminate chelotropic elimination of sulfur dioxide to produce the. So, essentially the chelotropic elimination will be dealt with in the last portion of the pericyclic portion, and for the time being assume that this is also a concerted reaction to produce the orthoquinodimethyl. Here is an example of a Hoffman elimination. This is essentially a 1,4 elimination of the amine. The hydroxide base abstracts the hydrogen from this methyl, producing a carbanion here. That carbanion undergoes rearrangement with the elimination of the trimethylamine, for example, to produce the orthoquinodimethyl. Finally, this is a orthosilylated ammonium salt. The fluoride ion essentially attacks the silicon because silicon is fluorophoric in nature, fluorophilic in nature. So, the fluoride ion attacks the silicon, producing trimethylsilyl fluoride, and in the process it undergoes the elimination of the amine to produce the orthoquinodimethyl. Orthoquinodimethyl's reaction with the Diels Alder fashion with the dimethylacetylene dicarboxylic acid is shown here. It produces the dihydronaphthalene derivative. The dihydronaphthalene derivatives are generally converted into the naphthalene derivative by reaction with DDQ, which causes the dehydrogenation of this particular molecule. So, the orthoquinodimethyl, which is also termed as orthoxylylene, can be produced in several methods as shown in this slide, and it can in situ be trapped by a dienophile, which is the dimethylacetylene dicarboxylic acid in this case, to produce the Diels Alder adduct, which is shown here. Now, benzene is a very reactive dienophile. Benzene can be produced in several ways. Some of the methods are shown here. Starting from anthralinic acid, for example, when anthralinic acid is treated with pentyl nitrite or isoamyl nitrite, it undergoes diacetization to produce this zwitterionic carboxylate diazonium salt. This, on strong heating, eliminates nitrogen as well as carbon dioxide to produce benzene as the intermediate. The benzene so produced can be trapped. We will see the trapping by Diels Alder reaction in a little while. The benzene can also be produced by the treatment of orthofluorobromobenzene, for example, using butyl lithium. When this molecule is treated with butyl lithium, initially a halogen exchange reaction with lithium takes place. So, the CBr bond is broken and you generate a carbanion, which is the lithium carbanion salt is what is produced. That carbanion undergoes elimination of the fluoride to produce the benzene as the product. Alternatively, orthotrimethyl silylated phenol triflates can be and made to undergo 1,2 elimination process. The full fluoride essentially attacks the silicon, producing trimethylsilyl fluoride. In that process, the triplet is eliminated to give the corresponding benzene as the intermediate. The benzene that is produced using this methodology, if it is produced in the presence of a strong dienophile, then it is capable, in the presence of a diene, then it is capable of undergoing a Diels Alder reaction. In fact, the Diels Alder reaction between anthracene and the benzene is known to produce the triptycene, which we have seen earlier, for example. In this particular case, the diphenyl substituted isobenzofurane undergoes the Diels Alder reaction to produce this bicyclic, also bridged bicyclic system. Deoxygenation using zinc produces the diphenyl substituted anthracene as the final products. So the anthracene can be made by the deoxygenation of this particular intermediate here. Alternatively, the benzene can be trapped with the furan as a dienophile. Furan is not a very reactive dienophile, but with a reactive it's not a very reactive diene, but with a reactive dienophile such as benzene, it can undergo Diels Alder reaction to produce the 2,2,1 oxo-bridge bicyclic system of this kind. Fulvene can be made to react with the benzene, for example, in a Diels Alder fashion to produce the molecule that is shown on the right hand side of this sequence of reactions that are shown here. You have already seen that the ketene does not undergo Diels Alder reaction with cyclopentadiene, for example, to produce the 2,2,1 bicyclic ketone of this kind. It rather undergoes a 2,pi cycloaddition reaction, in other words 2,pi suprafacial, 2,pi anterofacial cycloaddition reaction to produce the cyclobutanone derivative, which is shown here. So one cannot make the bicyclic ketone of this type by means of a Diels Alder reaction with the ketene as a methodology. Alternatively, one can use ketene equivalents. One such example is shown here. A monosubstituted cyclopentadiene, for example, reacts with nitroethylene at a very fairly low temperature, because this is a very reactive dienophile. Nitro-substituted ethylene is an extremely reactive dienophile. It undergoes Diels Alder reaction to produce the endoselective Diels Alder adduct, which is shown here. With several derivatives, this has been tried, and this Diels Alder adduct can be made to undergo oxidative Neff reaction using tertiary butyl hydroperoxide, vanadilyl ACAC as the catalyst, for example, using tertiary butoxide. What happens is, essentially in the presence of tertiary butoxide, this hydrogen, which is an acidic hydrogen, is removed and you form the nitronate. The nitronate undergoes, this will be C double bond N kind of a compound is what is going to be produced when the anion is generated here. That nitronate anion is essentially oxidized, the carbon nitrogen bond is oxidized to the corresponding ketone. So if you look under Neff reaction, you will be able to see NEF Neff reaction, you will be able to see the mechanism of this particular reaction. This is an oxidative cleavage of a secondary nitro compound to the corresponding ketone under basic condition, under oxidizing condition. So nitroalkene is actually acting as a ketene equivalent because it produces the ketone which would have otherwise been obtained from the reaction of the ketene with the cyclopentadiene. These are again two examples of ketene equivalent. Alpha chloroacrylonitrile can be used as a ketene equivalent. It is a fairly strong dienophile. It reacts with cyclic dienes like cyclopentadiene and cyclohexadiene and so on, producing the corresponding Diels Alder adducts which are shown here. In the Diels Alder adduct, when it is treated with potassium hydroxide in DMSO or using sodium sulfide and potassium, essentially under basic condition, the carbon halogen bond is removed by a OH by substitution reaction. Once the OH is produced, it is essentially a cyanohydrine is what is produced. The cyanohydrine is nothing but a masked form of the ketone. So under basic condition, the cyanohydrine undergoes the loss of cyanide to produce the corresponding ketone. So 2,2,1 bicyclic as well as 2,2,2 bicyclic ketones can be easily synthesized using alpha chloroacrylonitrile as a ketene equivalent by choosing the corresponding diene, which is either cyclopentadiene or cyclohexadiene, as shown in these two examples. Vinyl sulfones are also fairly powerful dienophiles because of the electron withdrawing nature of the sulfone group. They act as dienophiles in Diels Alder reaction. Couple of examples are shown here. For example, the diene, which is this particular diene derived from alpha pinene, undergoes Diels Alder reaction with phenylvinyl sulfone at 150 degrees. Nearly quantitative yield of the corresponding diene Diels Alder adduct is formed. This can be either dehydrogenated to undergo aromatization of this ring to produce the benzanulated system, which is this particular system here, or the the carbon sulfur bond can be reductively cleaved by desulfination reaction. Phenyl sulfenic acid is produced, and as a result of that, the carbon hydrogen bond is substituted with the carbon sulfone bond is replaced by a carbon hydrogen bond, which is a reductive elimination of the phenyl sulfinate in this particular case. Similarly, when the reaction is carried out with the cyclohexadiene of this kind, the corresponding Diels Alder reaction is produced. Reductive cleavage gives you this particular molecule in high yields. Alternatively, the carbanion can be generated at this carbon because of the acidic nature of the carbon hydrogen bond next to the sulfone group here. So the carbanion so produced is trapped by an electrophile, which is this particular bromide, producing this substituted derivative. Finally, the carbon sulfur bond is cleaved reductively to give this molecule in about 80% yield. These are molecules which are used for further synthesis as intermediate stages in the total synthesis of some compounds. Now let us go into multiple Diels Alder reaction. We have already seen that benzoquinone can undergo multiple Diels Alder reaction to give products of multiple Diels Alder reaction. Now this diene is nothing but a dimer of cyclopentadiene. It can undergo Diels Alder reaction twofold, once here as well as once here. The initial Diels Alder reducts are two products can be formed depending upon whether it is endoselective or exoselective with respect to the second cyclopentadiene. So the first cyclopentadiene has undergone a Diels Alder reaction in an exoselective fashion in this particular case and in an endoselective fashion in this particular case. Now that puts this diene in close proximity to this particular dienophile. So that Diels Alder reaction between this 1 and 4 carbon and this 1 and 2 carbon essentially produces this bridged bicyclic system. On the other hand, the Diels Alder reaction between this diene and this dienophile essentially produces the second bridged bicyclic tetracyclic system of this kind, for example. Now you can see here where the dimethylacetylene dicarboxylic units are placed. Here it is placed between the two cyclopentadiene rings. So it is undergone 2 times the Diels Alder reaction. The acetylene dicarboxylic acid has undergone 2 times Diels Alder reaction, once with the cyclopentadiene on this side, another time with the cyclopentadiene on this, as if the dimethylacetylene dicarboxylic has come in between these two cyclopentadiene rings to undergo twice the Diels Alder reaction. On the other hand, in this particular case, it has undergone only once the Diels Alder reaction to produce this bridged cyclic system of this kind. Instead of carbon dienophiles, one can have also tetraatom dienophile, as illustrated in the case of diethyl acetodicarboxylate. The diethyl acetodicarboxylate, of course, produces only one kind of a Diels Alder reduct, which is structure of which is shown here. So the first Diels Alder reaction essentially produces something like similar to this intermediate, except here you have a nitrogen-nitrogen single bond instead of the carbon-carbon double bond. That further undergoes Diels Alder reaction to produce the second bridged bicyclic system that is shown in this particular case. So these are examples of multiple Diels Alder reaction. There is one more example. Here the bis-furan 2,2-cyclophane undergoes Diels Alder reaction twice with the dimethylacetylene dicarboxylic acid to produce this fairly complex bridged dioxo-bridged derivative in this case. You can see here the dimethylacetylene dicarboxylate essentially lies between the two furan rings, so that this furan ring can initially undergo Diels Alder reaction, and the second furan ring can also undergo the Diels Alder reaction with the remaining double bond arising out of the first Diels Alder reaction to essentially saturate the carbon-carbon triple bond into a saturated sp3 carbon in this particular instance. So this must be the intermediate that is produced. This intermediate so produced can now undergo Diels Alder reaction further with the furan and the diethyl acetylene dicarboxylic acid residue that is present in this molecule in this case. This is a very fascinating example of synthesis of a molecule called pagodane. Pagoda are the structures that you see in Southeast Asia, and this is one structure, molecular structure, which resembles the pagoda. One can look at the internet and see what pagoda actually is in terms of the structural feature. It will resemble something, architecture would resemble something similar to this particular structure. This molecule has been synthesized after several steps, involving several steps. This has two diene unit pointing face to face to each other. The Diels Alder reaction with maleic anhydride essentially produces the Diels Alder adduct, which puts this double bond in close proximity to the diene. Once again, the Diels Alder reaction between the diene and the dienophile essentially produces this complex framework, which is further transformed into the pagodine structure by Prince Bach in his elegant synthesis of this very fascinating molecule. Now, so far we have seen the Diels Alder reaction to give bicyclic systems and so on. Here is an example where the Diels Alder reaction initially produces a bicyclic system, but the bicyclic system is not a stable system. It readily undergoes elimination of carbon dioxide to give an aromatic target molecule. So, alpha pyrrone is used as the starting material here as the diene. Alpha pyrrone is this particular molecule. It undergoes Diels Alder reaction with acetylenic systems of this kind, essentially producing a CO2 bridged bicyclic system like this. Elimination of CO2 from this molecule is very facile for two reasons. One is it relieves the strain of this bridge. Secondly, the gain of aromaticity is the main driving force in this particular case. A chelotropic elimination of CO2 essentially produces the aromatic ring, which is ortho disubstituted aromatic ring in this particular case. Now, when the acetylene is part of a fancy structure like this, which is a silyl capped triacetylene structure of this kind, you can imagine that the molecule can undergo Diels Alder reaction 3 times, once here, and once here. 3 times it can undergo Diels Alder reaction with the elimination of carbon dioxide in each Diels Alder adduct to produce. So, essentially this is a portion which comes from the pyrrone derivative. This is a portion which comes from the pyrrone derivative, and carbon dioxide elimination essentially results in the formation of this silyl cyclophane, which is a very nice molecule here. So, this carbons between the two silicons, whatever the carbons that you see is actually the triple bonded carbon. The acetylenic carbons are present here in this molecule. So, essentially the reaction proceeds 3 times like it is shown in the top portion, because the molecule has 3 acetylenes to produce this nice cyclic cyclophane, which is silyl bridged cyclophane of this kind. Pyrrone can also undergo Diels Alder reaction with bis trimethyl stanyl acetylene to produce the corresponding ortho disubstituted bis trimethyl stanyl substituted benzene derivative in this particular case, and this is essentially carried out in refluxing bromobenzene at high temperature. So, the reaction leads to a Diels Alder adduct which eliminates carbon dioxide to give the aromatic system, as in the case of the top reaction that is shown here. This is another example where the phosphonate substituted acetylene is undergoing Diels Alder reaction with alpha pyrrone. Various substituted alpha pyrrenes have been made to undergo this Diels Alder reaction in producing the ortho diphosphonyl benzene derivatives in this particular case. The alpha pyrrone is also called 2-pyrrone. This particular molecule has been used to make a highly substituted aniline derivative, as it is shown in this particular example. The alpha pyrrone undergoes Diels Alder reaction with the acetylene diethyl acetylene dicarboxylate, which produces the Diels Alder adduct, which subsequently eliminates the carbon dioxide to produce the ortho disubstituted derivative, which is this particular derivative. Alternatively, it can also undergo Diels Alder reaction with this enamine. The enamine portion undergoes dienophile is this is a inverse electron demand Diels Alder reaction. In other words, this is an electron rich acetylene and this is an electron poor diene. So, this is electron rich dienophile and electron poor diene. So, it is an inverse relationship in terms of the electronic nature of this. Diels Alder adduct undergoes the carbon dioxide elimination to produce the corresponding highly substituted aniline derivative in this particular case. On the other hand, with phenylacetylene, can undergo Diels Alder reaction to produce the corresponding phenyl substituted derivative. The important thing is that these are highly substituted aniline derivative which can be further used for organic synthesis, and this is a general methodology to produce such highly substituted aniline derivatives from 2-pyrrone as the Diels Alder component in these reactions. Now, we have already seen the Diels Alder route to the aromatic system, because the Diels Alder reaction with an olefin produces a dihydroaromatic system which can be dehydrogenated using DDQ to produce the aromatic system, or the Diels Alder reaction with an acetylene can produce a dihydroaromatic derivative. This is a tetrahydroaromatic derivative and this is a dihydroaromatic derivative. Again, dehydrogenation using reagents like DDQ or selenium dioxide can result in the formation of the corresponding aromatic derivative. Let us see some examples of applications of these two types of reactions in organic synthesis. Now, alternatively, what you can have is you can have substituents which are leaving group substituents like the chloro, bromo, methoxy and acetoxy on the diene, such that the Diels Alder reaction with the olefin produces a tetrahydroaromatic derivative. This can undergo 1,4 elimination of the HX molecules twice to give the corresponding aromatic derivative, or this dihydroaromatic derivative can undergo the elimination of a HX molecule to produce this aromatic derivative. So, instead of doing a dehydrogenation, you are doing a dehydrohalogenation reaction in these cases to produce the corresponding aromatic derivative. This is something we have already seen, alpha pyrone undergoing Diels Alder reaction followed by elimination of carbon dioxide to produce this. On the other hand, alpha tetraphenyl cyclopentadienone, which is known as tetracyclone, can also undergo Diels Alder reaction with an acetylene. The intermediate 2,2,1 bicyclic system is very unstable. It undergoes decarbonylation reaction by the loss of carbon monoxide. This is a chelotropic reaction. So, under the thermal heating condition, this is an unstable compound. The driving force here is again aromatization and the loss of strain because of the elimination of the carbon monoxide molecule. So, it is a chelotropic elimination of carbon monoxide to produce the corresponding hexa-aryl or hexa substituted benzene derivative can be synthesized using this methodology. We will see some examples of this methodology in a few minutes. This is called 3-dendrolene. These are cross-conjugated molecule. You can see the diene portion here as well as the diene portion here. It undergoes Diels Alder reaction to produce the corresponding Diels Alder adduct, which is a vinyl substituted ene derivative. So, this is again can act as a diene derivative. So, with the dimethylacetylene dicarboxylic acid, it once again undergoes a Diels Alder reaction to produce a very specifically substituted naphthalene tetrahydronaphthalene derivative. The tetrahydronaphthalene derivative can be made to undergo dehydrogenation using DDQ to produce this particular substitution pattern of the naphthalene derivative, which is very important in organic synthesis. Now, the ester can be reduced with aluminum hydride, and the alcohol so obtained can be converted into the corresponding tetrabromide. So, the tetra alcohol which is produced by the lithium aluminum hydride is converted into the tetrabromide using triphenylphosphine bromine combination as the brominating agent. Now, this tetrabromide is treated with zinc dust. When it undergoes reaction which is a dehalogenation reaction, you form an orthoquinodimethyl derivative here and an orthoquinodimethyl derivative here, which can undergo double Diels Alder reaction once on this side. The orthoquinodimethyl derivative is not shown in the scheme of things. That is an intermediate that is produced by the reduction of zinc, the dehalogenation reaction of zinc with this dibromo compound. And again this dibromo compound will also produce the orthoquinodimethyl. So, the Diels Alder adduct of the bis orthoquinodimethyl is what is shown here. This upon esterification by treating the anhydride with methanol and sulfuric acid, the corresponding tetraester is produced. The tetraester is actually a tetrahydro benzoanthracene derivative, and that is oxidized to the corresponding aromatic derivative using DDQ. So, overall it allows you to produce very specifically substituted naphthalene or this kind of a tetracene derivative, angularly fused tetracene derivative very nicely with high yields in all the steps. Yeah, here is an example where the dehydrohalogenation and the elimination of methanol is taken as an advantage to aromatize this compound. The Diels Alder reaction between this trimethoxy substituted butadiene and the chloro substituted naphthoquinone, for example, takes place at room temperature to produce the corresponding Diels Alder adduct. Now, there is a hydrogen here which can undergo dehydrohalogenation, for example, to produce the double bond over here. There is a hydrogen here which can undergo methanol loss, 1,4-methanol loss. In refluxing pyridine, for example, the dehydrohalogenation produces HCl. The HCl can catalyze the loss of the methanol by protonation of one of the methoxy groups followed by proton loss from this position over here. 1,4 elimination of methanol is what is responsible for the aromatization of this particular ring. So, initially the dehydrohalogenation produces a cyclohexadiene, and from the cyclohexadiene you lose 1,4 methanol in the 1,4 position to give the corresponding aromatic ring system. So, from a naphthoquinone ring system, now you have produced an anthraquinone ring system by a benzonylation reaction in this particular case. These are some fascinating examples of producing large cyclic compounds of this kind, polycyclic aromatic compounds of this type. This is tetraphenyl cyclopentadiene, which is otherwise known as tetracyclone, undergoes Diels Alder reaction to produce the corresponding Diels Alder product, which will be a carbonyl bridged 2-to-1 bicyclic system, as it is shown here. For example, the carbonyl bridged 2-to-1 bicyclic system is shown here. This undergoes decarbonization reaction to give the tetra-aryl substituted derivative. That is exactly what is happening in this particular example. The initially formed Diels Alder product with the loss of carbon monoxide aromatizes the central ring to the aromatic core, and the hexa substituted aromatic derivatives can be easily synthesized. The oxidative cross coupling of this carbon-carbon bond by a dehydrogenation reaction in the presence of oxidizing agents like ferric chloride essentially fuses these rings to produce the hexabenzocornene as the final product in this particular case. These are very fascinating molecule because one's imagination can be used, for example, to produce large polycyclic aromatic ring. This is called super triphenylene kind of a molecule. This is essentially produced by the triacetylene, which is shown here, with 3 equivalents or more of the tetracyclone as the derivative. The red portion in this particular structure essentially corresponds to this molecule, and the black portion essentially corresponds to the tetracyclone unit here, for example. So you can trace this carbon-carbon triple bond. This is originally a carbon-carbon triple bond. This was originally a carbon-carbon triple bond. Similarly, this was also originally a carbon-carbon triple bond. The molecule undergoes 3 times a Diels Alder reaction with the loss of carbon monoxide, which to give a Diels Alder product. The Diels Alder product itself is not shown in this slide. Instead, the fully aromatized cyclized compound is what is shown. The aromatization and the cyclization takes place in the presence of copper triflate as an oxidizing agent, in the presence of aluminum chloride as a Lewis acid, in a non-nucleophilic solvent like carbon disulfide in this particular step. A similar reaction is what is taking place here. The cyclopentadienone undergoes the Diels Alder reaction with this particular acetylene to produce the 2-to-1 bicyclic system, which loses carbon monoxide in refluxing diphenyl ether as a product. So you can see here this portion essentially comes from the diphenyl acetylene derivative in this particular case. So the consecutive rings, which are this particular 4 rings, for example, essentially come from the tetracyclone, and this portion essentially comes from the diphenyl substituted acetylene in this particular case. So what we have seen in this module is the synthetic application of Diels Alder reaction by several examples that are highlighted. Some of the reactions like the beltene and the triptycene and the kind of polycyclic aromatic hydrocarbons are very, very fascinating molecules. Of course, they have potential application in many areas also. I have not touched upon that. I hope you enjoyed this particular module. Thank you very much for your kind attention.